Look up at the night sky. What do you see? Twinkling stars scattered across the vast expanse of space, each one a distant sun, a fiery furnace burning trillions of miles away. Stars are more than just points of light. They are the building blocks of galaxies, the crucibles of heavy elements, and the engines that drive the evolution of the cosmos. From their birth in swirling clouds of gas and dust to their dramatic deaths, stars play a vital role in shaping the universe as we know it. Their stories are tales of immense energy, incredible transformations, and the ultimate fate that awaits all matter in the cosmos. Join us now on a journey through the wormhole as we explore the life and death of stars and uncover the secrets they hold about our universe and ourselves. Stars are born in vast, cold clouds of gas and dust scattered throughout galaxies. These clouds, known as nebulae, are the nurseries of stars where gravity draws matter together, igniting the fires of nuclear fusion. Within a nebula, dense clumps of gas and dust begin to collapse under their own gravity, forming protostars. As a protostar's core reaches a critical temperature of about 10 million degrees Celsius, nuclear fusion begins. Hydrogen atoms fuse together, forming helium and releasing enormous amounts of energy, marking the birth of a star. These stellar nurseries, often illuminated by the light of newborn stars, are breathtaking sights. They are cosmic gardens where the seeds of new stars are sown, ensuring the continued evolution of galaxies and the universe itself. Once a star achieves nuclear fusion, it enters a long, stable period known as the main sequence. During this phase, which constitutes the majority of a star's lifespan, it fuses hydrogen into helium in its core, releasing a steady stream of energy. The Sun, our own star, is currently in its main sequence, about halfway through its estimated 10 billion-year lifespan. The length of a star's main sequence lifetime depends on its mass. Massive stars burn through their fuel much faster than their smaller counterparts. As a star ages on the main sequence, it gradually exhausts the hydrogen in its core, triggering a series of events that will ultimately determine the star's fate. The transition from the main sequence marks a turning point in a star's life, leading to a variety of possible outcomes, each more awe-inspiring than the last. The way a star dies depends on its mass. Low-mass stars, like our Sun, end their lives relatively peacefully, while massive stars go out with a bang, leaving behind exotic remnants. When a low-mass star runs out of hydrogen fuel, its core contracts and heats up, transforming it into a red giant. Eventually, the outer layers are ejected into space, forming a planetary nebula, a glowing shell of gas and dust. The core of the red giant, now a white dwarf, slowly cools over billions of years, eventually fading into a black dwarf. Massive stars, on the other hand, experience a more violent end. When a massive star exhausts its fuel, its core collapses rapidly, triggering a supernova. Supernovas scatter heavy elements into space, seeding the interstellar medium with the building blocks of new stars and planets. The remnants of supernovae can take various forms, including neutron stars and black holes, some of the most extreme objects in the cosmos. Supernovae are among the most spectacular events in the universe. These cataclysmic explosions occur when massive stars exhaust their nuclear fuel and their cores collapse under their own gravity. As the core collapses, it releases an immense amount of energy, creating a shockwave that blasts the star's outer layers into space at incredible speeds. This explosion can outshine an entire galaxy for a brief period, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. Supernovae enrich the interstellar medium with heavy elements, essential for the formation of new stars, planets, and even life itself. The Crab Nebula, a remnant of a supernova observed in 1054 AD, is a testament to the power of these explosions. Its intricate filaments of gas and dust, still expanding outward, continue to captivate astronomers and reveal insights into the processes that drive supernovae. Neutron stars are the remnants of supernovae that occur when stars with masses between 8 and 20 times that of our Sun explode. These objects are incredibly dense, packing a mass greater than the Sun into a sphere only a few miles across. The intense gravity of a neutron star crushes its protons and electrons together, forming a sea of neutrons. Some neutron stars, known as pulsars, emit beams of radiation that sweep across space like cosmic lighthouses. These beams are produced by the star's rapid rotation and its powerful magnetic field, which can be trillions of times stronger than Earth's. Pulsars are incredibly precise timekeepers, with some rotating hundreds of times per second, making them invaluable tools for astronomers. The study of neutron stars provides a glimpse into the extreme conditions that exist in the aftermath of supernovae and sheds light on the fundamental nature of matter and gravity. Black holes are perhaps the most enigmatic objects in the universe. Formed from the remnants of the most massive stars, black holes possess gravity so strong that nothing, not even light, can escape their grasp. When a star with a mass greater than 20 times that of our Sun exhausts its fuel, its core collapses indefinitely, creating a singularity, a point of infinite density and zero volume. Surrounding the singularity is an event horizon, a boundary beyond which nothing can return. Black holes are invisible to telescopes, but their presence can be inferred by their effects on surrounding matter. Supermassive black holes, millions or even billions of times more massive than our Sun, are thought to reside at the centers of most galaxies, including our own Milky Way. These behemoths play a crucial role in the evolution of galaxies, influencing star formation and shaping the distribution of matter. Our galaxy, the Milky Way, is home to billions of stars, each with its own story to tell. While most of these stars are too faint to be seen with the naked eye, some shine brightly enough to be visible from Earth. Among our closest stellar neighbors is Proxima Centauri, a red dwarf star located just over 4 light-years away. Proxima Centauri is part of a triple star system along with Alpha Centauri A and B, which together form the brightest star in the constellation Centaurus. Another nearby star, Betelgeuse, is a red supergiant located in the constellation Orion. Betelgeuse is nearing the end of its life and is expected to explode as a supernova sometime in the next 100,000 years. These nearby stars provide valuable insights into the diversity of stellar populations in our galaxy and offer a glimpse into the processes that govern the lives and deaths of stars. The Sun, our very own star, is a yellow dwarf star located about 93 million miles from Earth. It is the center of our solar system, providing the light and heat that sustain life on our planet. The Sun's energy is generated by nuclear fusion in its core, where hydrogen atoms are converted into helium, releasing vast amounts of energy in the process. This energy is radiated outwards, eventually reaching Earth as sunlight. The Sun's magnetic field plays a significant role in its activity, giving rise to sunspots, solar flares, and coronal mass ejections. Despite its importance to life on Earth, the Sun will not last forever. In about 5 billion years, it will exhaust its hydrogen fuel and begin to expand into a red giant. As we venture beyond our solar system, we encounter a vast and diverse array of stars, each with its own unique characteristics and evolutionary path. Proxima Centauri, our closest stellar neighbor, and Betelgeuse, a nearby red supergiant, offer intriguing glimpses into the lives and deaths of stars beyond our Sun. Proxima Centauri, a red dwarf star located just over 4 light-years away, is much smaller and cooler than our Sun. Despite its diminutive size, it is known to host at least 2 planets, one of which, Proxima Centauri b, lies within the star's habitable zone. Betelgeuse, in contrast, is a red supergiant nearing the end of its life. This massive star, located in the constellation Orion, is expected to explode as a supernova sometime in the next 100,000 years. When it does, it will be a spectacular sight, visible even during the day and outshining the full moon. The study of these nearby stars provides valuable insights into the diversity of stellar populations in our galaxy and offers a glimpse into the processes that govern the lives and deaths of stars beyond our own. The life and death of stars are inextricably linked in a cosmic cycle of creation and destruction. The death throes of massive stars through supernovae seed the interstellar medium with heavy elements, the building blocks of new stars, planets, and even life itself. The material ejected from dying stars enriches the surrounding gas and dust clouds, providing the raw materials for the formation of new generations of stars. These new stars in turn will live out their lives, eventually returning their own material to the interstellar medium, continuing the cycle. This cosmic recycling process ensures that the universe is constantly evolving, with each generation of stars contributing to the richness and diversity of the cosmos. The heavy elements found in our bodies, such as carbon, oxygen, and iron, were forged in the hearts of stars that lived and died long ago. From the ashes of stellar death arises new life, a profound reminder that even in the vastness of space, nothing is truly lost, but rather transformed into something new and wondrous.